Now let's define P and NP. So there is a class of and here from now on we are going to talk only about decision problems, not about optimization problems. Now P is nothing but set of all decision problems for which there is a algorithm which solves the problem in order of in a polynomial time, right? So P is nothing but set of all decision problems for which there is polynomial time algorithm to solve them. So write it, P is nothing but set of all problems for which there is polynomial time algorithm to solve the problem itself, right? And now there is one more class called as NP. So people think that NP is not P. That is wrong. So you might think that the set of all problems for which there is no polynomial time algorithm is NP. No, that is wrong. The set of all decision problems for which there is a polynomial time verification algorithm is NP. Okay, it is the common mistake. Many people think that P means polynomial time and NP means non-polynomial time. Even though the frame, no one has ever expanded the NP as non-polynomial, even though intention is same, but then reading it that way is wrong. So we really don't know anything about NP problems. What we only know is these are the set of all decision problems whose solution can be verified in polynomial time. So the way you should specify it is NP is set of all decision problems. So even P is also could be written as the same thing, right? It is also set of all decision problems. Set of all decision problems for which there is a polynomial time algorithm to solve them. That is called P, right? And NP is set of all decision problems for which there is a polynomial time verification. Polynomial time verification, right? So what is the relationship between P and NP is, maybe you could think about the problems of P like this. The problems of P is, I'm just telling you some examples in the problem P class. So what is a P class? We are talking about only decision problem. Remember, we are not talking about the optimization problems. We are talking about the decision problems only, right? And in decision problems, what do I mean by P is we should be able to solve the decision problem in polynomial time. For example, given a graph, let us say the decision problem is there a minimum cost spanning tree whose weight is at most 10, right? Can you solve this problem in polynomial time, or can you answer yes or no for this question in polynomial time? We could answer it. How? We already have a algorithm which is for optimization algorithm. You can either use Prim's algorithm or Kruskal's algorithm, which runs in polynomial time, and find out the answer, right? And then we could verify whether that answer is right or wrong in again polynomial time, right? Let us say using Kruskal's or Prim's algorithm, you got the solution whose minimum cost spanning tree is of weight 9. And now they are asking, is there a solution which is having a minimum cost spanning tree whose weight is at most 10? Since you are able to answer that question with 9, therefore the answer is yes. Therefore what can you say? Yes. So for this one, there is a polynomial time algorithm. In fact, the polynomial time algorithm is Prim's or Kruskal's itself, right? For this one, there is a polynomial time algorithm. So this problem belongs to the class P, isn't it? And maybe given a knapsack problem, not 0-1 knapsack problem, normal knapsack, right? Is there any normal knapsack means fractional. Given a fractional knapsack, which means fractions are also allowed, is there any solution whose profit is at least 10? If this is the question, if this is the decision problem, can you answer this problem in polynomial time? Yes, in fact, we could answer the problem in polynomial time. We have answered it. How? Go back to the greedy fractional knapsack problem which I dealt with, right? There I told you that the time complexity is going to be n log n. Why? Sort out all of them in the increasing order of profit by weight ratio, decreasing order of profit by weight ratio. For that sorting, it is going to take n log n, and then pick up each element and try to put it in the bag. And for the last element, you put the fraction, right? Therefore, what is the time complexity? Order of n log n. So we are able to solve the problem or find the optimal solution in n log n time. Now let us say the solution you got is 20, which means the profit you got for a problem is 20, right? And what is this question they are asking? Does it see, and whenever I am saying this, they have given already a specific instance of the problem, given a specific graph, we are talking about this, given a specific problem of knapsack, we are talking about it. Now we already have a profit of the solution which is having a profit of 20, and now they are asking, do you have any solution which is having at least 10? If you already found out it is 20, then at least 10 is simple, right? Therefore you are going to say yes. If the question would have been, what if it is at least 5? Then the answer would be no. Anyway, either you are able to say yes or no in polynomial time. Therefore this problem also falls in polynomial. In fact, all the problems which we have seen before that dynamic method using greedy and divide and conquer are all going to take order of polynomial time algorithms, right? Therefore they are all actually P class: sorting, searching, and spanning trees, traversing, everything. Almost many problems that we have discussed which are having polynomial time algorithms are all P class, right? And now NP. NP means these are the set of all problems for which there is a verification algorithm, which means given the solution to a problem, you should be able to verify the solution in polynomial time, right? So if you are able to solve a problem in polynomial time, you will be able to verify the solution in polynomial time. How? You don't look at the solution at all, you try to solve it completely, then it is nothing but in polynomial time you could do it. Therefore every P problem, which means if you can solve a problem in polynomial time, you can verify the solution in polynomial time, isn't it? It is very simple. Therefore see, we are able to do a big thing. What is the big thing? Finding out the solution itself. That big thing itself we are able to do in polynomial time. Then why can't we say the do the small thing? What is small thing? See, it is like this. You are able to write the answer for a question. That is nothing but solving the question. And now given a question paper and the answer also, if they are asking you, check whether this answer is right or wrong, it is very simple, isn't it? Therefore if you are able to solve the question in polynomial time, then you will be able to verify the answer in polynomial time. So for every P class problem, there will be a verification algorithm which runs in polynomial time. So every P problem falls in NP problem. Along with this, there will be extra problems in the NP. Think about it. Every problem which is in P will also be in NP. Along with them, there are extra problems in NP. For example, traveling salesman problem. In traveling salesman problem, what happened is we failed to find out any polynomial time solution, but then given a solution we can verify it in polynomial time. Just now we did it, right? Therefore traveling salesman problem falls in NP but not in P. Why not in P? Because we don't know the polynomial time algorithm which can solve traveling salesman problem yet. We cannot say that there is no polynomial time algorithm. We don't know it yet. Got it? And then what about the 0-1 knapsack? For 0-1 knapsack also we are not able to find out the polynomial time algorithm which can solve it. But then give me a solution to the problem, I can verify it. Therefore this problem also falls in NP. Got it? Now what is the relationship between these two is, if a problem is in P, definitely it is in NP. If it could be solved, it could be verified in polynomial time. But if a problem is in NP, it is not yet known, or no one has ever proposed any algorithm for such a problem, for these kind of problems, so that we could put them in P. So there are at least now some problems existing which we know to be not in P but in NP. But in future, if someone solves it in polynomial time, then this one will go there, right? But as of now, they are not in P, they are in NP. So what is the relationship between these two is, if I write NP here, then P is going to be here, right? So in some way, the problems which are not in P and NP, which means NP minus P as of now are intractable, which means as of now we don't have any polynomial time algorithms to solve those problems. As of now these problems are intractable, right? But we don't know whether these problems could be solved in polynomial time, or we don't know whether these problems can never be solved in polynomial time. Since 1971 till this date, this question has been open, which means will anyone be ever able to propose a solution for this kind of problem, traveling salesman problem, which is not in P, in a polynomial time? That question no one has answered. No one is ever able to produce any polynomial time algorithm, nor they are not able to prove that no one could give such a solution in the future. Therefore the question is still open. Many researchers are still working on this, and they just believe, most of them believe like this, most of them believe that this P is present inside inside NP, which means P is a proper subset of NP, which is what most of the researchers believe, but there is no proof yet. But since 1970s till this time, these many researchers are working on it, and they continuously fail to prove that we could find a polynomial time algorithm for these problems. Therefore we started believing that there is no proof. We are just believing that maybe these problems might never be solved in polynomial time, which means maybe this one is right. Putting the problems of P inside NP, and in such a way that there are some problems outside P but in NP, is actually turning out to be right, which means we are believing it that way. What is this thing? We believe it, but there is no proof yet. Got it? So now we shall see what happens and how to prove that some problem is hard, some problem is easy, and how to prove that actually this P is present inside NP and not that P and NP are equal. So one question which is open is, P, is it equal to NP? This question is still open. Now in order to answer this, I know two questions have to be answered. Whatever problems are lying outside this, they all have to be solved in polynomial time. If we could solve all of them in polynomial time, then all these problems, now when all the problems which are outside this can be solved in polynomial time, then all of them will move into P. Then we can say P equal to NP, right? So if you have to prove that P equal to NP, you solve everything which is outside this in polynomial time, right? Or if you want to prove that P is not equal to NP and P is a proper subset of NP, which we believe now, if you want to prove this one, then what you should do is, you should show that there is at least one problem outside P for which no one could ever produce a polynomial time algorithm. Either you could solve everything in polynomial time, or you take at least one problem and show that it can never be solved in polynomial time. This open question can be answered. What is the open question? The relationship between P and NP. No one knows it yet, right? If you have to win that Turing award, maybe you prove it either this is true or this is true. Maybe it might take a lifetime. I don't know. Maybe since till now no one is able to prove it, I am thinking that if someone has to prove it, they have to dedicate their life for this, and I am not very sure. It is like a halting problem, right? Which means even by the end of your life, you don't know whether you will halt and then say this, and maybe I don't know whether it is worth trying for it. People have moved on, which means even without solving this problem, they are able to solve many real life problems using approximations, right? So yes, one kind is people who are doing research in algorithms, they are supposed to work on such problems. What they do is, one way of working on in this area algorithms is, they will take some NP complete and NP hard problem. I'll talk about shortly. They will take a very difficult problem which is known to be difficult, and now they will try to give a close approximation. This is one kind of research going on, right? So if you are interested in having a research career, then maybe you could read about them in depth, right? Whatever I am teaching you is going to be good enough, but then even if you want to learn more, if you want to be in algorithms, in masters, you do more work on this, okay? Now let's talk about the continuation of this, the NP completeness, the actual thing.